Welcome back to the final video about smart pointers. Today we're going to be going over how we can create an actual memory leak in Rust. Yeah. How is that possible, you might ask? Isn't Rust supposed to be super memory safe? Reality is, yeah, Rust is pretty memory safe, but by tweaking the rules of ownership, with what we've been doing with RC and RefCell, we can actually create two types or nodes that reference each other. Let me pull up a diagram to show what we're going to do. So we're going to have our handy dandy cons list here with nodes A and B, and we're going to point B to A here, and then we're going to also point A back to B. We're going to do this by wrapping our RC values in ref cells. So if you remember with our regular cons list, we just have RC. This time we're going to be wrapping it in a ref cell so that we're able to edit what our current node is pointing to next. In this case, we're taking A and we're updating the ref cell to point back to node B. As you might guess, we could still lose ownership of both A and B, and they'll still take up memory because they both have strong references to each other. That makes sense, right? So we could have our let B equals B, our node B here, and that's just pointing to this node. So this would be a strong reference here, and then we have let A equal our A node here, and that has a strong reference to that. And let's say that this is in some sort of function, right? Like a create graph function that we were dealing with earlier. At the end of create graph, what if we just dropped A and B and didn't return anything? With what we were doing before, with if we didn't have a reference cycle, then our strong reference count to B would drop to 0. Same, or would drop to 0, and A would drop to 1. But because B now drops to 0, B calls its cleanup and it drops its reference to A. So A's strong reference count is going to be equal to 0 as well, along with B. So both of these get dropped from memory nice and easily. But if we went ahead and called this same like create graph function, and then we just dropped our references to these nodes. So first of all, let's say B gets dropped, all right? So we no longer have that. We only have, but we now have, instead of 3, we have 2, or 1, instead of 2, we have 1 reference to B from A. And we will go ahead and drop A here, and we still have 1 reference to A from B. So even though we don't have any way of accessing this memory anymore, this chunk of memory where A and B live still is going to be, or I guess they'd be 2 separate chunks of memory, but they would still be active and would not be freed up. So we've gone ahead and, like I pointed out earlier, we have a ref cell with our handy dandy cons list, so we're able to change what we're pointing to as our next item in the cons list. And we went ahead and just implemented this tail method here, which makes it easier to basically grab out this value if we're indeed dealing with a cons variant. Now for the fun part, like we just did here, we're gonna, right now we have nothing. So let's go ahead and create a node A, which is gonna be a new RC pointer to a cons list. Cons, and we'll just have the value be 5 here. And we're gonna just point it to nothing. And we're gonna do that by first making a ref cell, a new ref cell. And we're gonna point to a new, because again we're wrapping this within a reference counter, so it gets a little hairy with all the nested parentheses and whatnot, but I believe in you, I believe in me, we believe in each other, right? So we got new here, and we're going to just pass in nil to say that we've reached the end of the list. And then we're going to do the same for B. And this time the value is going to be 10, if I can type. And at this point in time, we have two, or should I say one strong reference to A. One and one strong reference to B. And actually, what we're going to do here is, instead of it being the end of the list, we're going to point B to A. So we're going to do RC clone, and then a reference to A. So at this point in time, our strong ref A is equal to 2 because, like we just touched on, we have our let A here, and then we also have B pointing to A. And we have one strong reference to B. Now, using this handy dandy tail method that we have, we're going to go ahead and yoink out the ref cell for A and point that to B. So we're going to do that by doing a little bit of pattern matching. So I'm going to say if let sum, and we're going to say it's going to be called a link, is equal to the tail of A. Then we're going to dereference that link, and we're going to borrow the ref cell, or sorry, we're going to borrow mutually first, and then we're going to dereference that mutable borrow, and we're going to, oh, there goes Arnold, basically say that our tail, we're going to assign it to a strong reference to B, and we're going to do that through RC clone B. So that's all we've done here, is we've done the second step right here. All we've done is take A and point it back to B. And again, as a reminder, we use our dereference operator here to say the value inside of our ref cell, inside of our ref cell should equal a strong reference to B, since borrow mute gives us a mutable reference and not the link itself. And now to prove the point, we're going to print out A and B's strong reference count. And I'm just going to yoink some code here. And we're going to do a cargo run. And I'll go ahead and make this a little bit bigger. And as you can see, A and B both now have two references. And even though at the end of our main function, thankfully our program just exits, but if our program was to still keep on running here, or if we even just wrap this in a scope here, A and B are still gonna be valid, or should I say the values, the nodes A and B with the values 5 and 10 are still gonna be alive in memory even here, because they are both pointing to each other and their strong reference count never reaches 0. So pretty much any time we combine refcell with RC, or in other words, we're allowing a value to have multiple owners, Arnold, and making that value mutable. So we have multiple owners through RC, and then we're allowing ourselves to change what we're pointing to through refcell. We are inviting a reference cycle bug into our code. We don't really have an elegant solution for this when it comes to the con list here, unfortunately, since we do need each node in the cons list to own its next value. That just makes sense. And we don't want to have, owning we don't want this to be a reference to the next value in the cons list, because then we'd need to keep the owned values somewhere in memory, right? It'd just be easier if we had one reference to ahead, and then we were able to reference the other values in the cons list by just going down the linked list. So in this case, again, we don't really have an elegant way of fixing this. It'd be up to the developer to basically at runtime make sure that we don't have a reference cycle wherever it's appropriate, or just make sure that your code never creates a situation where a reference cycle happens with a cons list. but we'll look at another data structure where we do have an elegant solution for reference cycles. So let's imagine we're creating a tree in Rust, and let's say we want the ability for a node to be owned more than once. So in other words, we want to be able to say something like here we have A owning B, but we may also want a strong reference to B in our stack somewhere. So we could say like let B equals B, and we'd want a strong reference to our B, maybe because we want to mutate it in some way, but we want to be able, in our case, have multiple references to nodes. So in that case, we're going to need RC. Our node definition is going to be an RC, right, of node. Arnold says hi. And we also want our parent to own multiple children nodes like we have said here. So we're going to wrap our RC value in a vector. So we're going to have a vector of RCs of nodes. And then finally, we want to be able to add or remove nodes from our tree. So like in this case, we maybe want to delete C for whatever reason or add D. So the easiest way to do this is to allow interior mutability of our vector through the ref cell smart pointer. So we're going to actually wrap our vector in a ref cell. We didn't wrap our vector within a ref cell like so, then we'd have no way of editing B if we did not have direct ownership of B. So like let's say we have ownership of A. Let's say we have let A equal A. Let's say we have ownership of A. We can get B through our vector of RC nodes, but remember that RC holds an immutable reference to our nodes. So we'd be able to access B, but reference counter doesn't allow us to edit the value inside that it holds. So that's why we're getting a ref cell to essentially this this B node here. I'll just make it super clear. So A, again, if we did not have ref cell, it would be a collection, in this case vector, RC node, and then our RC node is immutable. We get an immutable reference to B. If we wrapped our vector in a ref cell, then we'd be able to edit the values of B's children, because B's children are wrapped in a ref cell and we're able to get a mutable reference to B's children that way. We're going to have a node, and first of all, we're going to have this derive the debug trait, so we're able to easily peek into it through the dbg macro. And we're going to have a struct node, and we're going to have a value, just going to have it be a number, and then we're going to say children of this node. It's going to be a ref cell, and we want multiple children, so we're going to wrap this in a vector, our RC nodes in a vector as well. So I'm going to go ahead and say that we want an editable vector. That's what we're doing for ref cell, editable vector, and each of these vector elements should be a reference count to, or RC smart pointer to node. So I'll go ahead and start building our tree out. We're going to have a leaf and a branch node, so we're going to start with the child node, which is the leaf. So we're going to say leaf is going to equal reference counter, a new one, and we're wrapping a node in this reference counter. And we're going to have a value of 3, and then we're not going to have any children, but we still need to make a ref cell with an empty vec here. So we'll do new and an empty vector. Not a semicolon, semicolon there. And then we're going to have our branch node. It's going to be a new reference counter with a node, and this time the value is going to be 5. And we're going to set the children to be a ref cell with a vector that has a reference to leaf, and we're going to use RC clone for that. So we're going to go ahead and say ref cell new, and what we're putting in the ref cell is a vector, and the first element in this vector is going to be a strong reference to leaf, like so. Now we have an easy way to traverse down the graph by simply looking at the children vector on branch. Just to make this perfectly clear, we have branch, which has children on it, and then we have leaf, so that can point easily down, like so, to our leaf node. But what if we wanted to traverse up the array? We don't really have a really good way of doing that right now. So let's say we have our leaf node, like we only have a reference to it. We don't have anything here that can point us back to branch. So what we could do is we could add a parent field in our node structure, but we're going to very soon run into the reference cycle problem if we do that. So if we updated our node to be value children parent with ref cell RC Arnold says hi, that's my cat. In case you haven't, and this is your first time watching, Arnold's my cat, and he pops in the videos every now and then, so sometimes he causes some antics, but cat antics aside, we're gonna, if we did this, we're gonna always have one strong reference to the child node and one strong reference to the parent node, even if we don't have any sort of reference to either node. So that's going to look something like, let me get rid of my dock there. So right now we have parent with child, and we have a way to reference it. If we have a child that points to parent, then we run into the same thing that we were running into the previous video, where we have a reference. So if you remember from the last video, we had B pointing to A, and then A's tail, the next item in the list was B. We kind of have the same thing going on here, where we have a parent node that points to child, and then child also points to parent. They're kind of in, they're holding on to each other. They both own each other, so they're never gonna be considered invalid, or their strong reference count is never gonna reach 0, in which case that means we can have no references to it in our code, but they'll still take up memory, which is a memory leak. What we can do to solve this problem is making the reference from a child to a parent, so this arrow here, a weak reference instead of a strong reference. So what does that mean exactly? A weak reference basically lets us have a reference to an RC value, which our parent node will be wrapped in, without holding ownership. It's kind of like a good old regular reference with our ampersand here. Like if we're doing an immutable reference to at parent, it's kind of like the same idea here, except we can't be sure if the value actually exists because we don't have a strong reference to that value. That is, we can have one or more weak references to an RC value even when there's 0 strong references, which effectively means that the value has been dropped from memory. So parent could be dropped, like let's say we have let parent equals parent, and then this scope ends, right? So our strong reference count is actually 1 here instead of 2. And then let's say that we drop our scope, so this no longer is valid, goes out of scope. And since we only had one strong reference to parent, parent gets dropped. And then in this case, because our only strong reference to child was from parent, then this gets dropped as well. You could also say, like, let's say that our parent value got dropped, right? But we still have a strong reference to child, like we had somewhere in a different scope, like let child equal child here, our node, and like, again, this is the child node here, and it just points to, just make this clear, that it points to this node, right? Like our child points here, and our parent went out of scope, we now don't have a reference to parent, but we're able to try to upgrade our weak reference to a strong reference, and we're going to go over that a little bit later in the video. But basically, all we really need to know at this point is that child does not own parent, so parent can be dropped. So let's go ahead and see this in action. We're going to bring the weak type into scope. It lives in the same module as RC, so I'll first go ahead and say RC and weak. And then we're going to update our parent definition to say, hey, we want a weak reference to our parent node instead of a strong reference through RC. And again, another way of putting it is that it makes sense that a parent should always own its children here. So this is a parent node, it should own its children, but a child shouldn't own its parent. That's what we're saying here. We will then update our parent and child nodes to reflect these changes. So I'll go ahead and say for our leaf, our parent, we're not going to have a parent quite yet. So say parent is going to be ref cell new, and then we're just going to have an empty value for our weak reference. We're able to do that. Even though we specified a type of node, we're able to basically say, hey, this holds a type of node, but it's empty for now. We will then go ahead and do the same here. A new weak reference of type node. And then we'll go ahead and update our leaf node because we have this ref cell, right? We're able to go ahead and reach inside of this ref cell and update our weak reference. So I'll go ahead and say that our leaf dot parent, and then we're going to get a mutable reference to that interior value in the ref cell, right? So borrow mute, if I can type leaf, and then that's going to equal, and then in order to get a weak reference from our parent node, so that would be branch here, in order to get a weak reference from it, we're going to call, instead of RC clone, we're going to call RC downgrade. And that basically gives us a weak reference to branch. And then again, we need to use the dereference operator here because we're dealing with a reference here and we want to actually update the value inside of that reference. And if we wanted to get the value out of our new leaf, now that we actually want to get the parent out of it, we can do this. So what we're doing here is we're calling borrow on our ref cell, because remember, parent is a ref cell that wraps a weak value, and we get that reference and we call upgrade on it. And what upgrade does is it optionally returns a strong reference to our parent. So in this case, we do have parent, so we're going to go ahead and put parent back in, and this would be a strong reference. Now, this strong reference is only valid for the lifetime of this function because we passed it in as a argument into print line. So as soon as print line is finished printing out our strong reference to parent here, it's going to drop that strong reference, and we'll continue to have our weak reference, and we can call leaf.parent.borrow upgrade again to get another strong reference. And if we wanted the strong reference to last for the life cycle, the lifetime of main, we could put in strong ref here, and now strong ref is gonna have this reference to the parent via our leaf node here. Now we're just going to get rid of this, and we're going to just prove our point here that we can indeed get the leaf parent out of our print line statement there. So as you can see, it's wrapped in an option as well, because we may or may not be able to get a strong reference from our weak reference, right? So there is our parent node right there. Now, if we did not go ahead and assign this strong reference, we're going to get a none value, as you can see there. Or another way we can get none is if we wrapped our parent node within its own scope here, because again, we only have one strong reference. We made a weak reference here, but we only have one strong reference. We dropped our strong reference at the end of this scope, so our leaf.parent doesn't point to anything. Whoops. And I can go ahead and prove this with cargo run. Leaf parent equals none. Well, that's a wrap for today's video. In summary, we went over how combining RC and refcell, if this was RC here, RC, can cause reference cycles where two or more data types point to each other, meaning if our only real reference to one of those data types goes out of scope, those values would still remain in memory since they all strong reference each other. In other words, if A owns B, like I did here, and B owns A, then A and B will never be dropped from memory, even if they should be. That's it for smart pointers. Next up, we're going to be looking at multi-threaded programming. Ooh. Be sure to check out this video's exercises in the repo.